Assalamu alaikum, everybody. My name is Ahmed Al-Hussein, and today we are going to try to understand the wave polarization. It's a topic in electromagnetic waves course, and it's presented by instructor Dr. Hussein Atiyah. So our outlines of this presentation, we will try to cover the basics of wave propagation, and we'll try to understand what is polarization, and we will see the three different types of the polarization. We have a linear polarization. Also, we have a circular polarization and elliptical polarization. And then we will move to the application of polarization. So, what is the basics of wave polarizations? First, we have the electrical field represented by the letter E, and the other main component is the magnetic field, which is represented by the letter H. And when we cross multiply both of them, if we assume that the electric field is propagating or moving across the y plane, and the magnetic field is moving across the z plane, by cross multiplying them we will get the direction of propagation, which is along the x direction. As you can see here in this picture, if you point your finger along the y direction and then curl them toward the z direction, your thumb will point to the direction of the propagation of the wave, which is in this case the x direction. As you can see here, the electric field is represented by these red lines and these red waves, and the magnetic field is represented by this blue wave. And the angle between them, between the electric field and the magnetic field, is always 90 degrees. They are always perpendicular to each other. So, what is polarization? Polarization describes the orientation of the electric field in a wave. At any point along the wave, the tip of the electric field vector traces a pattern over time. This pattern is what determines the polarization of the wave. As you can see here, this is the tip of this trace the tip of the electric field vectors, and it form a wave that describes that represents the polarization, which is the third wave here we have, and it is the total represent the total wave of Ex of t and Ey of t. So the first type of polarization we have is the linear polarization. In the linear polarization, which is the simplest form, the electric field oscillates along a single axis. In this example, it is oscillating along the positive z direction, or along the z axis, and remains in this plane as the wave propagates. This common in many everyday applications such as radio waves and other applications that we will discuss later. Notice here that the magnitude of the linear polarization, the magnitude of the electric field, could be similar or different magnitude. What differs from the other two types is the phase difference. The phase difference represents the difference between the angle of or the phase of the EY, the electric field along the Y direction, and the electric field along the X direction, as it's shown here in the simulation. So when we have a phase difference equal to 0 or pi or multiples of pi, we have a linear polarization, and the magnitude could be similar or different. In this case, as long as the phase difference equal to 0 or multiple of pi's, the polarization will be linear. Here in this video, in this simulation, you can see clearly that when we have a 0 degree in the phase difference between Y and X, the polarization, which is represented in this vector here, is linear. There is no circulation or any other or any of the other types. And when we have 180 degree or pi radian, the same thing will be applied, but in a different direction. So when we have the phase difference equal to 0, we call these two fields in phase. And when we have it equal to pi, we call them out of phase, and which can be proven here, as you can see, one in the positive X direction and the other in the negative Y direction. While in the other case, when they are in phase, they both have the same sign, positive or negative. The other type is circular polarization, and circular polarization happens if the field components along the X and Y axis have equal magnitude, and both are or the phase difference between them is equal to pi over 2. We will talk about the right hand circular polarization meaning and the left hand circular polarization later on. So as you can see here, we have same amplitude and we have a phase difference of negative 90, because remember, we take the phase of Y minus the phase of X. Since we have 90 degree in the phase of X, the phase difference between them would be minus 90. And you can see here that when we have minus 90 phase difference, which means a negative phase difference, we call this circulation, or the direction of the circulation of the polarization, is counterclockwise, which means it is a right hand circular polarization, because when you curl your fingers along the direction of the polarization, your thumb should point towards you, And when you use your right hand, this case is valid. The other case is when we have minus 90 degree, where the circular, the direction of the polarization is going clockwise. In this case, we will use the left hand to curl along the y direction, along the polarization direction, and the thumb will be pointing towards us. The other case, on the last case, is the elliptical polarization. As you can see here in the video, the angle here is different, and the phase difference is not 0 and not pi. In fact, the phase difference could take any values except 0 and pi. But what about pi over 2? Well, if we have a similar magnitude of both of them, both for EX and the EY, we cannot have a phase difference of pi over 2, because in this case it will be circular polarization, as we saw in the previous example. So as long as the phase difference is not pi over 2, we could have any magnitude, even similar magnitude. And when we have phase difference of pi over 2, we should have, or we must have, a magnitude which are different from each other. And this, as we said before, if we have a positive phase difference, we'll have a right hand elliptical polarization, and when we have a negative phase difference, we will have a left hand elliptical polarization. As you can see here, we set the phase difference to be minus 60, and you can see clearly that it is an elliptical shape, and the direction of the polarization is a right hand elliptical polarization. As you curl your right hand fingers with the direction of polarization, your thumb should point towards you. The other case is when we have a difference of positive 60, the left hand should we will use the left hand to curl our fingers along the polarization direction, and your thumb should be pointing towards you. So this is the other case. When we have a 90 degree, we should have a different amplitudes or magnitudes of both of them, for X and for Y. As you can see here, when we set X to 0.5, we got an elliptical shape, and the same rule applies for the left hand and right hand elliptical polarization. So I will mention some of the applications of polarization, which is used on the daily basis, and without going into its complicated details. So the first application is the antenna, and the polarization helps antennas in transmitting and receiving signal more efficiently. The other example is satellite, which uses circular polarization to transmit data without interference, regardless of orientation. And the last example we have today is the LCD screens, which use polarized light to display images. Also, I forgot to mention that regarding changing the frequency, and the other parameters, it won't affect the polarization, but it will affect the basic components of the waves, such as the wavelength and the phase velocity of and the period of the wave. As you can see here, when we change to 500 hertz, the period here changed to 2, and when we change the relative permittivity, the phase constant changed, as you can see. Thank you for watching, and I hope you benefited from this explanation. Assalamu alaikum.